We're going to talk about matrices in this video. We are going to use matrices first to solve the systems of equations that we've been working with most recently. Matrices are only going to be used to solve the linear systems. We're not going to be able to solve the nonlinear systems with the matrix, or we're not going to go into how to do that. We are only going to use matrices to solve linear systems of equations. When we're solving those systems of equations, we use substitution, we use elimination. Wasn't terrible with two variables. It took us a little bit of time, but it wasn't terrible. When we got to three variables, it took us a considerably longer amount of time. We could still do it. We never even attempted one with 4 or 5 or 6 variables, and at the time I kind of alluded to the fact that it's going to take a lot longer. It's a lot more tedious of a process to solve something using substitution or elimination with 5, 6, 7, 20 variables. But we should be able to do that. And so a matrix is going to assist us with that process. That is not to say that is all matrices are used for. Matrices have many uses. And so let's talk about the definition of a matrix first. A matrix is simply a rectangular array of numbers, letters, or symbols arranged in rows and columns. And we indicate that matrix with brackets. You'll always see matrices with brackets just to indicate that it is a matrix. And so maybe we have the matrix with the numbers 1, 2, 3, and 4. For whatever reason, I have a matrix just holding those numbers. Or maybe I have alpha, beta, zeta, and a plus symbol. For whatever reason, that's the information I need stored. And what I just said is exactly what a matrix does. It stores information. Matrices are great at taking large data sets or large tables and storing all that information very concisely. If we think about our system of equations, that is a large set of data, especially the larger those things grow. And so matrices store that very efficiently, and it also makes it easier to work with. So in a way, I sometimes will compare this to almost synthetic division. Synthetic division, remember, if we had a big long division problem, we said, well, as long as we're dividing by a linear divisor, we could take that, we could strip off the variables, we could store it all very concisely in this synthetic division. It stored all that information very concisely. Matrices kind of do the same thing. They take all those variables, they take them off, and they store that information very concisely. So let's go ahead and use a matrix to help us solve a system of equations. I'm going to start just by writing down a system of equations. So we have the equation x minus y plus 2z is equal to 9. We have x plus 2y minus z is equal to 6. And the third equation, 2x plus y plus 2z is equal to 18. Now we're going to be able to use matrices to solve any number of variables. I'm going to start with 3 because that's something we've done before. And 2 just seems a little bit too easy for a matrix. So let's start with 3 variables and we'll build from there. The first thing I need to know is how to put this thing into matrix form. And this is actually incredibly simple. All we're going to do is pull off the coefficients. So the coefficient on my x is a 1. The coefficient on my y is a negative 1. The coefficient on my z is 2. And then what it was equal to is 9. Now, if I just write it like this, I'm going to get a little bit lost, perhaps, of what side is equal to the other side, especially if these things weren't all on the same side, if it wasn't properly lined up with all the variables on one side, the constants on the other. So what I'm going to do is I'm going to draw a vertical bar in my matrix where the equals is. And what this is called now is an augmented matrix. Don't really need to know the name for this class, but just so you've seen it, augmented matrix. Augmented matrix, very simply, is just a matrix with a vertical line in it or this bar in it. And that bar could represent an equal sign. It could represent any number of things. It could be we're dealing with a data set, maybe where we have male and female, and we want that vertical bar to split up the two sides of the data. Or maybe we have, we're measuring marbles and we see red, blue, and green. So that could just be splitting up those different categories. It's just a way to categorize our data. So this first line represents the first equation. We can see that that first position represents x, the second is y, the third is z. So from here on out, I just want to be consistent. So we have 1x, 2y, negative 1z, 6 is my right-hand side, my equals. Then in the third equation, I have 2, 1, 2, and 18. So like I said, a very simple process. The thing we want to make sure of is that we have everything's set up correctly before we get to put into the table. So all our x, y's, and z's correctly on the left-hand side, correctly arranged, and then the constants on the right-hand side. So now what we're going to do is we're going to use the matrix to solve our system. And so our goal is going to be to get to a point where our matrix looks like this. If we think about why we want the matrix to look like this, what this is saying is we have 1x, 0 y's, 0 z's equals a. Or simplified, x is equal to a. The second line is saying 0 x's, 1 y, 0 z's equals b. Or y is equal to b. Third line is saying 0x, 0y, 1z is equal to c, or z is equal to c. So once we get this line of diagonals, one's on the line of diagonals and zeros everywhere else, we have our solutions. It doesn't matter how big this matrix gets. Anytime we see that pattern where we have ones on the diagonal, however many we have, zeros everywhere else equals, however many of these things we have, then we have every single variable solved for. What this is called is a row-reduced echelon form matrix, or RREF for short. Row-reduced echelon form, where we have ones on the diagonal, zeros everywhere else. That form of a matrix will allow me to solve my matrix. A couple things to note in this process. The process for going from our initial matrix to this form, that process is called Gaussian elimination, or Gauss Jordan elimination. I really need to add in the Gauss Jordan elimination. The reason I need the Gauss and the Jordan elimination, you can put a matrix into just reduced echelon form, which means we have ones on the diagonal, zeros underneath, other stuff on top. And that allows us to solve for that final variable, but not the others. So I'm not going to spend a great deal of time on that. I'm just going to be shooting to get to ones on the diagonal, zeros everywhere else, using Gauss Jordan elimination. Gaussian elimination puts it into reduced echelon form, but Gauss Jordan elimination gets me to my final solutions. If we think about the processes that we are allowed to use, what am I going to be allowed to do to this matrix? Well, let's think about what we're allowed to do to the equations. When we were solving systems of equations, we said, hey, we can add, subtract lines. We can add, subtract equations, rather. If we think about what the equations have become, they become lines. So we're allowed to add and subtract lines. That's one thing we can do. What else are we allowed to do with our equations? We're also allowed to multiply through or divide through by anything we would like. And so if we think about our lines, we can multiply or divide through by any number. We are not allowed to just add a number to both sides. So notice I said add, subtract lines, or multiply, divide by a number. I can't just say, hey, I'd really like this to be a 0, let me add a 1, because all that's doing is it's adding a 1, and adding 1 to both sides doesn't help me. This is really a y, it's not a 1. That's why we have to add, subtract lines. So we're going to see that as we go forward. And then there's a third thing that we can do that we don't really think about a whole lot, which is that we can always just rearrange the order of the equations if we would like to. We don't have to leave these things in this order. And so if we think about what that would mean in terms of our lines, we can just rearrange lines anytime that we would like. If I want to list this line first, I can do that, or list this line first, that's fine. So we can always add, subtract lines. And we'll see if I can guess where that stuff was before. Add, subtract lines. If my program will recover. There we go. Sorry, we can rearrange lines. Rearrange lines. Can always rearrange lines when we see fit. All right, so this is what we're working with. I want to see the ones on the diagonal, the zeros everywhere else. I'm going to do this in a very methodical process, and this process will always work. If you're trying to jump around, occasionally you might come across a shortcut if you're jumping around, and that's fine if you're really comfortable with what you're doing, but I recommend not jumping around. What I'm going to do is I want to make sure I have a 1 in this first position, 0 is underneath. Then I'm going to move on to the next position. I'm going to actually move down a row too. I'm going to go 1 in this position, 0 is underneath. Then I'm going to get a 1 in that final position. Once I have the 1s on the diagonal and the 0s underneath, then I'm going to get back up and work on these getting 0. And we're going to see why that is. But what we've seen in the past is it's much easier to multiply or divide 1 and use a 1 to cancel something out than it is anything else. And that's why I'm shooting to get the 1s first. Now in that first position, we already have a 1 there, so that's perfect. So now I need to get this to be a 0. And like I said, I can't just subtract a 1. Because if I just subtract 1, this is really an x, and x minus 1 isn't. That's not going to help me. I need to subtract an x. Well, where is there another x? There's an x here, or there's an x here. There's two x's here. But it's much easier to use the 1x. So I'm going to subtract the first line. I'm going to leave the first line alone for right now. I'm going to leave it exactly as it was. And I'm going to subtract that first line. 1 minus 1 is 0. 2 minus negative 1 is 3. Negative 1 minus 2 is a negative 3. 6 minus 9 is negative 3. So again, we did 1 minus 1, 2 minus negative 1, negative 1 minus 2, 6 minus the 9. If it helps you to see it, write out what you're doing. 2 minus 1, that's fine. Turn it into that full statement. I just, a lot of times, I'll leave off what I'm working with because I know this is the third line. So I just do my subtract, the third line, subtract whatever I need to do. All right, so at this point, I have the 0 underneath there. I'm going to get a 0 here as well, so I can work with multiple lines at once. If I want to get a 0 here, again, I can't just subtract a 2. That's not going to work because 2 isn't the same as x. But I do need to subtract 2 times that first line. Could I have used the second line? Sure. But a lot of times I'll just work off the same line. So we'll have 2 minus 2 times 1. That's 0. 1 minus 2 times negative 1. That's going to turn into a plus 2. So 1 plus 2 is 3. Then we have 2 minus 2 times 2. So that's 2 minus 4, that's a negative 2. And we have 18 minus 2 times 9. 2 times 9 is 18, so 18 minus 18 is 0. So our third line, we have 3, negative 2, and 0. All right, next, I'm going to leave that first line alone for right now. We have our 1 with our zeros underneath in the first column. That is perfect. But I need this thing right here to become a 1. I need 1, 0, 0, 1, 0, and then the 1 finally here. But for right now, I'm going to work on this becoming a 1. There's multiple ways we could do this, but the easiest way to get your 1s is always just to divide by that number. Could I, if I wanted to, say subtract from this 2/3 times this? Yes, I could do that. That'd be a pain in the butt. I could. Could I have added 2 times the first row to this? I can't do that. And the reason for that, if we add 2 times the first row, notice I'm adding a 2 to the 0. I'm going to change that 0. I don't want to change the 0. So I need to make sure if I'm adding, subtracting anything, I'm doing it to the line that has the 0 in its column, the matching zeros, because I don't want to change anything there. However, like I said, much easier just to divide everything by the 3 because I can always divide both sides of an equation by the same thing. So 3 divided by 3 is a 1. Negative 3 divided by 3 is negative 1. Negative 3 divided by 3 is negative 1. Now, oftentimes I'll wait till this next step till I manipulate this number, but I do need this to be a 0, and right now I notice they match up so nicely. So I could just go ahead and subtract that second line, and they'll cancel out right away. I'd have 0 minus 0 is 0. 3 minus 3 is 0. Negative 2 minus a negative 3 turns into a plus. Negative 2 plus 3 is 1. And then 0 minus the negative 3 turns into a 3. So we're just subtracting everything in this row from this row. And that's how we get to this third line. Now I have the 1s on the diagonals, the 0s everywhere else. I'm going to start working on getting 0s above. So if I want a 0 here, I could subtract 2 times the third row. Why am I using the third row? Why not the second row? I could use the second row, but again, it's easier to use a thing that has the zeros. I guarantee I'm not changing anything else, and that's important in some cases. Here, it wouldn't matter if I changed that second item, but it's easier to do just the one calculation rather than the two. So when we do this, we have 1 minus 2 times 0, which is 1. Negative 1 minus 2 times 0, which is negative 1. 2 minus 2 times 1 is 0, as we wanted. And then the 9 minus 2 times 3, that would give us 3, because 9 minus 6 is 3. In the second row, I have the 0 and the 1 as desired, but I need this to be a 0. The easiest way to do that is just to add the third line. This is another spot where I wouldn't want to say add half of the first line because I'm adding things back into the zeros or the ones and I don't want to change this. So if I add the second and the third line, I'd have 0 plus 0 is 0, 1 plus 0 is 1, negative 1 plus 1 is 0, negative 1 plus 3 is 2. And then the third line is done. Notice it has the zeros and the 1 already perfect. So now the bottom two lines are done. We only need to worry about that top line. And I can fix this position by adding the second row. The arrow is just indicating that I'm done. I'm not changing anything. So 1 plus 0 is 1, negative 1 plus 0 is 0, 0 plus 0 is 0, 3 plus 2 is 5, and then we had the 0, 1, 0, 2, and 0, 0, 1, 3. And so we have an x value of 5, a y value of 2, and a z value of 3. Or we could say the point 5, 2, 3 solves the system of equations. We used a matrix. Now this is actually the exact same problem I did in the video with 3 variables with the linear solutions, the linear systems. It's the same first problem because I wanted to show you that we can get to the same place either way. Now I think right now you're probably a little bit slower with matrices over substitution elimination because you've done more of it. But towards the end there, I kind of was going a little bit faster, and I was showing you the speed at which you can do these. The key to matrices, it is something brand new. We're setting something up in a brand new way. So I think for that reason, it takes us a little bit longer. But once you really get comfortable at them, they become much faster than using the full equation. It's the same idea as that synthetic division. I'm not bothering to write down the numbers the variables each time on the numbers. It's going to speed me up greatly, and it's a lot easier to organize when it's all concisely written like this. So they really are efficient. I know some of you are probably sitting there saying this is way harder, but really the more you practice, the better you're going to get, and it becomes much, much faster, much, much easier than the systems of equations. This is one of those places that it's one of those skills we need to learn because we gain so much in the long run. If we're going to try and do everything with a system of equations, you're just going to get to a point where it takes way too long. If I give you something with 5 variables in it, it's going to take me half an hour to do that problem. There's not a good way to do that. There's not all of a sudden a magic way that you're just going to get fast at it versus matrices. If I give you something with 5 variables, it's going to take me 5 minutes, but it's going to take me 5 minutes and not half an hour. You really do gain speed the more time you spend on them, and you gain efficiencies the more variables there are. To go from 2 to 3 variables with systems takes a long time. To go from 2 to 3 variables on a matrix, not a whole lot of time. To go from 2 to 10 variables on systems would be a pain in the butt. To go from 2 to 10 variables on a matrix, not terrible. All right, let's take another example. This time I'm going to take, let's see my equation. Let's take the equation negative 7x minus 3y plus z is equal to 13. Sorry, negative 13. Then we'll take a x plus 9y plus 2z is equal to 19. And finally, negative 4x plus minus 5y plus z is equal to a negative 14. Let me just make sure I have all this written down right. Don't want to do something that gets real ugly too fast. X, 9y, 2z, 19, and negative 4, negative 5, z, and negative 14. Perfect. So not that we couldn't do it if I'd mix those up, I'm just trying to keep it to where the numbers don't get too ugly on us. So that's why I just want to make sure I had the problem I intended to do. So first thing I'm going to do is convert this over to a matrix form, and we saw this is relatively easy. -7, -3, 1, -13. We have a 1, 9, 2, and 19. We have a -4, a -5, a 1, and the -14. All right, first step's the same. We want that very first position up here in the top left to be a 1. And so we could divide by the -7. Remember I said to get 1s, division is always the fastest thing. If we want to get the 0s, that's when we're adding or subtracting our line. So it's very formulaic, right? We're doing the same thing every single time. To get the 1s, divide. To get the 0s, we add, subtract lines. However, there was a third step that I said we were allowed to do, which is always rearrange. So I see a 1 in that first row. Why don't I just move that up to the top, and then I don't have to do any math, and I already have the 1 in that first position. I'll just drop that second line down to the first line down to the second line, so -7, -3, 2, and -13, -4, -5, 1, and -14. So just by doing a simple little rearrangement, I haven't done any real math here, I already have a 1 in that first position. Now I'm going to get the 0s underneath. So if I need a 0 here, I'm going to have to add 7 times the first line. If I need a 0 here, I'm going to have to add 4 times the first line. And that first line is going to stay the same. So we have 1, 9, 2, and 19. I'm going to have a -7 plus 7 times 1, which is 0. -3 plus 7 times 9, well 7 times 9 is 63. And subtract 3 from it, it's -60. -2, and then 2 times 7 is 14. It's not -2, it's +2, and then 14 is going to give me a 16. And then -13 and 7 times 19. I'm going to use a calculator to help me out on this one. -13 plus 7 times 19. We get 120 there. So our numbers have gone pretty large pretty quickly, but we'll live with it for now. The next row, we're going to do 4 times the first row. So -4 times, or -4 plus 4 times 1 is 0, as desired. -5, and then 4 times 9 is 36. And so if we have -5 and 36, that would give us 31. 1 and 8 is 9. And then -14, and then 4 times 19. So again, let me use my calculator here. -14 plus 4 times 19 is going to give me a 62. All right, at this point, I need this to be a 1. So we have to divide here. I'm going to leave the first row alone for now. To get this to be a 1, I'm going to divide by itself. I'll leave the third row alone in this case. Remember in that first example that we did, I went ahead and got that to be 0, but it's going to be real hard to add 31 and 60 in some way to get a 0. I'm going to go ahead and just wait till I get the 1 there. It's much easier to convert a 1 to a 31 than a 60. So 0 divided by 60 is 0, 60 divided by 60 is 1. 16 over 60, I can definitely simplify that if I want to. I know 4 goes into, both those 4 goes into 16 4 times. 4 goes into 60 15 times, so 4 over 15, and 60 goes into 20 twice. And then the last row, like I said, I'm just going to leave it alone for just a second. And so now this last row, I need this to be a 0, and the easiest way to do that is subtract 31 times the second row. So we have 1, 9, 2, 19. We're going to have the 0, the 1, the 4, 15 stays the same. Clean that up a little bit. And then the 2. And then we'll have 0 minus 0 is 0. 31 minus 31 is 0. 9 minus 31 times 4 over 15. So that one's going to need to get a common denominator. I'll write it down just so I can see what I'm doing. So 9, if we were to find a common denominator, would be 135 over 15, I'm pretty sure. Let me just double check that before I move on. 124 rather, over 15. And again, you can use your calculator to help you out. So everything I'm saying out loud, we can just use a calculator to do this. I'm just doing it all in my head. And so we get the 135 minus the 124, and that gives us 11 over 15. And then this 62, I'm going to have a 62 minus 31 times 2. Well, that 62 minus 62, that is just 0. So even though we had some messy fractions in there, I need to get a 1 right here, so that means I'm going to divide it by itself. I have to divide by the 11 over 15. It's actually going to be a relatively simple calculation because I have zeros in all the other positions. So when I multiply 0, or when I divide 0 by anything, it's 0. We get a 1 there. And we get RZ to be equal to a 0. Now I need to get these to be 0, and the easiest way to do that in the first line is subtract 2 times that third line. Easiest way to get this one to be 0 is subtract 4/15 times the third line. Again, that seems really messy, but we're just going to be subtracting zeros, so it's actually relatively simple. 1 minus 0 is 1, 9 minus 0 is 9, 2 minus 2 is 0, 19 minus 0, and that'll give us 19. It should be a 19. And then the next row, we have 0 minus 0 is 0. 1 minus 4/15 times 0 is 1. 4/15 minus 4/15 is 0. 2 minus 4/15 times 0 is 2. And then the bottom row has stayed the same. And then the bottom 2 rows are done, notice now, because that bottom row has been done. We had the 0, 0, 1. The second row, we have 0, 1, 0. We need this top row to be 1, 0, 0. So the easiest way to do that is subtract 9 times the second row. And so we have 1 minus 0 is 1, 9 minus 9 is 0, 0 minus 0 is 0. 19 minus 9 times 2 is 19 minus 18 is 1. We have our 0, 1, 0, 2, and 0, 0, 1, 0. At this point, we have that x is equal to 1, our y is equal to 2, and our z is equal to 0. And so there is our solution. Again, that should look familiar from the first video. I'm just repeating a lot of the same examples to show you we get to the same place. And so the third and final example I want to do is another one that is just the same as that earlier video, the 3-variable linear systems. And should be coming up. And I will stress again, I'll take a second to stress that we can only do the linear systems. We're not doing anything with the nonlinears for right now. So we're just doing linears. To put a nonlinear into a matrix would take a lot more work. It's a lot more complex, and really they can't all go in very nicely, and it would not be the same process. We're just doing the linears. All right, so here is the last example I want to do. We're going to use our matrix. So I'm going to start by putting it into the matrix. We have 1, 1, 0, and 4. We have 1, 0, 1, 2. And we have 0, 1, negative 1, 5. All right, so we have everything written into our matrix. We have a 1 in that first position. We know we need zeros underneath. Now, here's one thing I was talking about. Don't try to work too far ahead. Move in that logical order. A lot of times I'll see students say, well, I'm going to go ahead and get this to be a 0 here, and then I'm going to have 0, 0, 1. So I might as well move that to the third line because I know I want 0, 0, 1. I don't necessarily want to move this yet. It's not that it will mess you up per se, but remember, when we're adding or subtracting rows, we're changing other things around it. So when I come in here and I subtract off that first line, I'm going to be changing that. That's not going to stay at a 0. So I'm not going to do any rearrangement. I'm just going to go ahead and subtract that first line. The third line is already fine. I have that 0 there. Maybe I'll want to move this up to the second line. That might be a smart decision because I have that 1 in that position, but I'm going to wait to see. Don't get ahead of yourself. Get your 1 in that first position, 0's underneath. Then move on to the next one, 0's underneath. Kind of say it's like walking down the stairs. You got to walk down the stairs. Once you get at the bottom, then we'll worry about above. Don't worry about getting to that last stair before you worry about that first stair, right? So I'm going to have the first line stays the same, 1, 1, 0, 4. Then the next line I have 1 minus 1 is 0. 0 minus a 1 is negative 1. 1 minus 0 is 1. And then 2 minus 4 is a negative 2. Notice how I changed that second position. It's no longer just a 0. And the last line is going to stay the same. At this point, I do want a 1 in this position, so it's not real hard just to change all those signs if I wanted to do that. Or you could just move this line up. I'm going to just go ahead and change all the signs, meaning I'm dividing by negative 1. That seems pretty easy to me. Doesn't matter though, if you were to switch lines. So 0 stays 0. The negative 1 becomes positive 1, the positive 1 becomes negative 1, negative 2 becomes a positive 2. In the third line I've just left alone for that half a second. Something should be kind of catching our eye at this point, one of those red flags, which is that left side is looking the same, the right hand side is not. I know I need a 0 here, so I'm just going to go ahead and continue with the matrix operations. I'm going to subtract the second line. Let's see what happens when we do that. So the first line stays the same. The second line is going to stay the same. Everything was looking good from those first two. In this third line though, I get 0 minus 0 is 0, 1 minus 1 is 0, negative 1 minus negative 1 is 0, 5 minus 2 is 3. Let's think about what that bottom line is telling us. It's telling us that 0 is equal to 3. 0x plus 0y plus 0z, or 0 is equal to 3. When is that true? That is never true. This tells us that there are no solutions to this problem. This is an inconsistent set of equations. So just like with our systems of equations, if we see that we end up with a statement where all the variables have dropped out, those two sides might be equal to each other. If they are, there's going to be infinitely many solutions. We have a dependent solution set. If the two sides are not equal to each other, we'd stop and we'd say that there is no solutions for that. Solving systems of equations is just one thing that matrices can do. So we're going to look at a few other examples in this class of how we can use matrices, how we can work with those matrices, what applications we can apply, and also what else can we use matrix for? What other places do they come up?